So I welcome you again, right? And we would like to proceed from our last uh, lecture, and unfortunately we could not conclude that because we had some important interaction in the auditorium. So now we have been talking about the frame of references, laboratory frame of references, and rotating frame of references. First, we talked about these two frame of references in classical world, and then we have been trying to understand the impact of rotating magnetic field on our quantum mechanical system. And our quantum mechanical system is the spin. The spin that is assigned to an electron. Electron has its own intrinsic angular momentum, and this intrinsic angular momentum gives what we call as magnetic field as a result of the magnetic moment of the electron. So now, what we have in quantum mechanical rotating frame of reference, now what we are doing here is that your frame of reference is rotating with respect to the rotation of the magnetic field. If you rightly remember the example that I gave you last time, that if you have two bodies moving in same direction, say for the sake of argument, with same velocity, the body A is at rest with respect to the body B, and the same thing is for body B with respect to body A. Now you have a rotating magnetic field, and at the same time the choice that we have is a rotating frame of reference. So you are coining your problem where you have a rotating magnetic field, and you are coining this thing with the rotation of the frame of reference. So what you are doing mathematically is you are translating your problem, which was time dependent previously. You are translating your Hamiltonian, which was time dependent previously. You are translating it into a time independent Hamiltonian. Right? So you can see the field appears static. It will appear static to the rotating frame of reference. Okay? So the dynamics simplifies. The dynamics involved in this problem simplifies, and the spin precession can be described with an effective magnetic field. Now go back to your laboratory frame of reference, okay, where your frame of reference is not rotating. Okay, if it is not rotating, now your problem is purely time dependent, and you are applying a magnetic field. Electron has its own magnetic field. The result of these two magnetic fields gives us what? It gives us precession. You remember the precession of angular momentum, right? But here, in this case, you are taking away the precession of the system, and your problem purely becomes a constant problem, because you have to calculate the effective magnetic field of your system. So this is how it simplifies our problems. So we can see time independent Hamiltonian. So you come up with a time independent Hamiltonian by choosing a rotating frame of reference. It simplifies solving Schrodinger's equation, and it reveals the resonance condition. See, if we go into the crux of the quantum mechanical systems, let's talk about the Bohr postulate. What Bohr postulate is? If you give some required quantum of energy to an electron, it will disappear from one energy level and it will appear in another energy level. That's the argument. It is not like that electron will have a flight from energy level 1 to energy level 2, because in quantum mechanics we don't have trajectories. If we don't have trajectories, then you have something that you can measure. But before measuring, you have lots of things in quantum mechanics. And these are lots of things are the result of superposition. And your system is in a state where you cannot say where the electron is. Is your electron in energy level 1 or is your electron in energy level 2? If you are giving some intermediate energy, you understand intermediate? Intermediate means that you don't have a transition, but you are supplying energy to the system. If you are supplying energy to the system, what is happening to the system? What is happening to your electron? Because you have only two states. The state 1, say in energy level 1, the state 2 in energy level 2. But, okay, if you give the sufficient quantum of energy to the electron, right? Say in hydrogen atom, the electron will appear in energy level 2. But when you will give an energy which is not equal to h nu, what's happening at that time? Your system remains in superposition. You cannot demonstrate that superposition. And finally, there is resonance. It is the resonance that makes a transition possible from one defined quantum state to another defined quantum state. Getting my point? So at some point, if you go back to photoelectric effect, what happens? You apply the electromagnetic radiation, okay? And you keep on increasing the frequency. Because up to certain frequency, you have no photoelectric effect, right? And what happens at threshold? What happens? There's a resonance. Something great happens. The electron comes out of the atom. Getting my point? Getting my point? Okay. So we can understand the phenomenon of resonance conditions easily when you take your problem from laboratory frame of reference to rotating frame of reference. So how can I intuit? How can I imagine here the fictitious thing that we have in classical world? So I have tried to answer that question. So in classical analogy, what we have the fictitious forces. Okay? Now in quantum mechanics, what we have the transformation. We have the transformation, and this transformation leads to effective terms in the Hamiltonian. Is this right? Okay? So the example of that is Rabi frequencies. We'll be discussing them in future. So you can see here, in the rotating frame, an electron exposed to a resonant magnetic field. Now you understand the resonant magnetic field. What it does, it exhibits the Rabi oscillations. As I told you if you give an intermediate energy to an electron so that the energy is not sufficient, so that electron can go from one energy level to another energy level, then what is existing there? They are existing, you can say there's a superposition. There are oscillations. Okay? And we call these oscillations as Rabi oscillations. Right? And electron has many probabilities. It can be anywhere. Right? Right? Okay. So what we have in the lab frame, we have the time-dependent Hamiltonian. In the rotating frame, we have transformed the Hamiltonian with these terms, what we call as Rabi terms. And what we have here? We have the effective magnetic field. And this effective magnetic field is a constant. So you are translating your complicated problem into a simple one. So to end this introduction, what we have rotating frame analysis is crucial. It has its future. If you go in the same framework, it can lead you, if you understand the phenomenon like magnetic resonance, you can understand quantum computing, you can understand spintronics, you can do research in these fields.
And it simplifies the understanding of electron spin dynamics under these rotating magnetic fields. Okay, now let's go with the mathematical argument. Okay, so what I have to do now, I have to go back here. Okay. Yes. Okay. I don't want it. When I have to write with this. Can I write? Come on, which tool I have to use to write? Yeah, this must be it. Yes, okay. So now what we have to go with this problem. So we have an electron, okay? Electron has magnetic moment, right? And we know what magnetic moment of an electron is, and we know its symbol, it's mu, okay? So what's mu? Mu is, it is E by 2m s. This is the magnetic moment of electron, right? This is the magnetic moment of electron. This is the magnetic moment that's associated with this spinning electron. E is the charge of electron, and m is its mass, and s is what is x? S, it is the spin, right? It's the spin angular momentum of the electron. Okay. Now, if I assume that my magnetic field is on a plane, right? I have a magnetic field, I'm applying this magnetic field to the system, and my magnetic field is B, okay? And this magnetic field can be written in terms of the components of the magnetic field, and I can write down some B naught times x cap cosine of omega t plus y cap sine of omega t. Right? As you know, if you have a vector in a two-dimensional plane, that is xi cap plus yj cap. And you can translate this x and y into your polar coordinates. And it will lead you to this argument. Well, B naught is the maximum value of the magnetic field, and it's a constant, right? So what you have the magnetic field, and you have the magnetic moment, okay? And what you can calculate from here, you can calculate the Hamiltonian. So how can you calculate the Hamiltonian? Now I have to go to the next page. How will I go? This one. Bottom right, where is that? I have tried that. Yeah? Okay, this one. You come here to show me. Come on, if you know, come on, come on. Come on. I'm using it first time, so that's why I don't know exactly how to go to the next page. Okay. I say this one. Okay, okay. So this we have to do, huh? Okay. Okay, so now if I have to calculate the Hamiltonian, H, interaction Hamiltonian for this system, that will be minus mu dot b. Right? And what is mu? Mu is E by 2m, and then you have S dot, for B I have B naught x cap cosine omega t plus y cap sine omega t. Fine? Right? Okay, that's the case. Now, if you rightly go back, we have already talked about Pauli's spin matrices. And instead of using the components here as x and x cap and y cap, I will be introducing the Pauli's spin matrices, right? So I'll be directly using Pauli's spin matrices. Have you written it down? Okay. Now, come on. So what I'll have, I will have H interactive. This is my Hamiltonian. This will be E by 2m, and then you will have B naught and sigma x cosine of omega t plus sigma y sine of omega t. Now I can introduce a constant here. If I use H interaction is E B naught by 2m H bar times H bar times the same thing, sigma x cosine of omega t plus sine of omega t. Is it clear? Now this thing, the bracketed term, this is a constant, we call it as a coupling strength. So it gives us the measure of strength because you have an interaction of external magnetic field with the spin angular momentum of the electron. So this EB naught by 2m H cross this E B naught by 2m H cross is equal to a constant omega. Now this is a coupling constant. This is a coupling constant. So how will my H interactive look like? It will look like H bar omega times sigma x cosine of omega t plus sigma y sine of omega t. Right? Is it fine? Okay. Now the point is that we are introducing a Hamiltonian, and that is a rotating, that too in the rotating frame frame of reference. Okay? So how do we write that? Now if I have to write that down, the problem that I have been discussing in the rotating frame of reference. So for that, what I will have H. Okay? H is, I will write down this equation the way you write Newton's second law of motion. Okay? So H will be U of t, H U of t adjoint, or you could call it dagger, minus IH bar U of t d by dt of U dagger of t. Where this U of t is what? It's a unitary transformation operator. Okay? So this equation will give us the resultant Hamiltonian in which you have incorporated what? the rotating frame of reference. Are you getting my point? Okay. So H, I should call it HROT, H rotating, or you may simply call it as H dash. Okay? So what you have the terms to calculate here. What is U of t? It's a unitary transformation operator, right? And what is this unitary transformation operator equal to? Can anybody among you tell me? Come on. Yeah. This U of t is e to the power of I omega t by 2 sigma, depending on the coordinate x of t. So this is my unitary transformation operator. Okay? And this operator is equal to e to the power of I omega sigma x t by 2. Where sigma x is your Pauli spin matrices along x. Right? Now, if I have to take its adjoint, what will be that? That will be e to the power of minus I omega by 2. Your sigma x will translate to sigma zt. You can do this as an exercise. Alright? Now, I can take the derivative of this adjoint of the unitary transformation operator. Because the equation that I wrote down for H rotation, in that you have the first term, that is U of t, then H U adjoint of t minus I H cross d by dt of U dagger of t, U adjoint of t. So what can you do here? You can take its derivative with respect to time, right? You can take the derivative. What will be the derivative? So that will be d by dt of U dagger of t. What will it give us? It will give us minus, it will give us I, it will give us omega, it will give us 2, it will give us sigma z, and it will give us U dagger of t. That's it. Okay? This is what you will get from here. I can move on the next page. Okay. So, what we will have? We have been calculating minus IH cross U of t. Is it U of t? Yeah. And we have calculated this thing as minus I. What was it? Come on. What was it? I omega by 2 sigma z, and so U of t and U dagger of t will give us 1. So what we will have, if we have not done any mistakes, so this will lead us to H bar omega sigma z by 2. This is term number 1, okay? This term was the second term of the rotating Hamiltonian. And what is this H cross omega sigma z by 2? What is it? It's a constant. Getting my point? Okay. Now what's the next term? What was the next term? Next term was U of t, h, and U dagger of t. And this h, you remember what was this h? What was it? So it is U of t yeah, what was this? It was H cross omega. Was it something like this? Okay, then inside what you had? You had sigma x cosine of omega t. Okay, then plus h cross omega sigma y sine omega t. And what will be outside? On outside you will have u of t dash. This is what is there. Is this clear? Okay. Now here you will do some framework of mathematics. So what you will see, you will have this u of t and u dagger of t for this term, and another u of t and u dagger of t for this term. Are you getting my point? Okay. When you will solve this, you will find that the result of this term comes out to be, the result of this term comes out to be h omega. You can do it as an exercise, okay? You can do it in your tutorials. You can work for it. So what is h rotational obtained from here? It's obtained as h cross omega, right? Plus h cross omega by 2 and sigma z. What's on the board now? A number. What is on the board? There is no dependence. You don't have a function. You have averaged it out and you have obtained a constant. So by introducing a rotational frame of reference to the problem of spin, which is basically a time dependent problem, very complicated to be solved if chosen in a laboratory frame of reference, this problem has boiled down to the numbers. Okay? I'm not sure about the result, but I'm sure about the constancy of the result. The result that we obtain by introducing the rotational transformation leads us to the constant Hamiltonian and gives us the information about that system. Okay? Any questions? Anything you want to explore here? You have anything you want to ask me, you can ask me. Come on. Yes? These symmetries have to be resolved using these unitary transformation operators. Because finally they should boil down. They will boil down, okay? You will not have the function between them. The way you saw that we calculated that derivative of adjoint of u of t, we obtained a constant, then we could take its value equal to a unit, its value equal to a constant. Right? So we should stop.